Hello, I'm Eleanor Wiley from Physics Partners, and in this short film we're going to look at current in series and parallel circuits and the moving charges which constitute current. This film is part of a series to help you with your physics teaching, especially if you're new to teaching, new to physics, or just looking for some new ideas. I'll focus on some of the common misconceptions that students have and give you some tips for introducing the concept. Feel free to pause, take notes, or rewind and watch again. But before we even start thinking about current, you probably want to teach your students about charge. In other words, static electricity. Students need to understand that there are two types of charges: positive charges, which cannot move about in solids, and negative charges, which are electrons that can be moved by rubbing different materials together. There are some classic experiments you can do involving plastic rods, but I'm going to show you a version using everyday materials. Here, I'm just using plastic straws, or you could use pen cases, resting on a bottle top. To begin with, the straws and the cloth have about equal numbers of positive and negative charge. But when I rub one of the straws on the cloth, I'm depositing some electrons from the cloth onto the straw. And there we can see a force of attraction between the positively charged cloth now, because it's lost electrons, and the negatively charged straw. If I rub both the straws together, then they're both picking up the same charge, and hopefully we should see that they repel one another. So the negative charges repel and positive and negative charges attract. Many of us like to get out the Van de Graaff generator when teaching static electricity. The dome allows a big build-up of charge, which shares its charge with anything touching it. Don't be afraid of a Van de Graaff. Look it up on Cleeps for some excellent ideas for great demos and, of course, safety advice. I don't have a Van de Graaff generator here, but this fly stick works in the same way. Electrons build up on the wand, and anything in contact with it gets a negative charge and gets repelled from the wand. So we've been looking at static electricity, but for current, we actually need the charge to flow. I can actually use the fly stick to move charge around. So I need two empty Pringles tubes. One I've connected to earth here. I've got the closed ends facing about 10 centimetres apart. And between the two, I've got the ping pong ball covered in kitchen foil hanging up from above. And what I'm going to do is I'm going to turn the wand on and put it inside and touch the base of the tube on the left. And so electrons are now being transferred to the tube on the left, and there'll be a negative charge building up on the base. With the ball, the electrons on the side facing the ball are going to be repelled round to the other side, to the right-hand side of the ball. So hopefully in a moment, it will actually come across, that's it, and pick up those negative charges and ferry them across the gap to the other side, where they're then carried to earth. And the same thing happens again, it keeps repeating. So we're actually using the ball to carry the charge across the gap. It's not actually current yet, but it's definitely a movement of charge. Because each electron is so tiny and stores such a small amount of charge, we need a macroscopic unit to measure that charge in. That unit is the coulomb. 1 coulomb is equal to the charge on 6 times 10 to the 18 electrons. The unit of current is the ampere, or amp for short. We can tell students that if a coulomb of charge passes a point in 1 second, the current is 1 ampere. What if 2 coulombs pass in 1 second? Well, then it's 2 amperes. You might like to pause the film and try these examples. Students should then be able to figure out the equation for themselves. Current is charge over time, or current is the rate of flow of charge. We've helped them understand the concept, and we've done some simple numerical examples before introducing the equation. Current has the symbol I, which can cause some confusion. This comes from the French intensité du courant. The symbol Q for charge comes from quantity of charge. I'm going to show you how current flows in circuits using this circuit building simulation from PhET. Here I have a series circuit with a cell, a resistor and ammeters to measure the current. One nice thing about PhET is it can show the charges in the wires. You can see that even with the switch open, the charges are already there throughout the wires in the whole circuit. It's a very common misconception that the electrons start at the battery and only enter into the circuit when the switch is closed. This is not the case. What happens now I close the switch is that they start moving everywhere all at once. Now, as we're looking at negative electrons here, they're repelled from the negative and attracted to the positive. However, for historical reasons, we describe conventional current as flowing from positive to negative, like this. As soon as this flow starts, we get a reading on both our ammeters, and note that that value is the same. Another common misconception is that current gets used up by bulbs or resistors, but it doesn't. The current is the same everywhere in a series circuit. However, the current does change if I increase the resistance. Now the value of the current is going down because increasing resistance means that it's harder for current to flow through the component. Current is always the dependent variable. A nice way to show this is with a rope loop. To model a circuit using a rope loop, you need a loop of rope and at least two people. The rope represents the charges in a wire, not the wire itself. Here I'm using a rope with flex in that we could consider as coulombs of charge. One person represents the power supply that provides a potential difference. They do this by pulling the rope around. Another person represents a bulb or a resistor by gripping on the rope a little. If I pull harder on the rope, modelling an increase in potential difference, the rope moves faster, modelling a higher current. If, though, the person gripping grips harder, with the same pull, the rope slows down, showing a decrease in current. This is also great for showing how the energy is transferred. The person pulling is clearly doing work on the rope to make it move, but the person gripping gets a warm hand due to the friction, which models the heating effect of current in the bulbs and resistors. While you're doing this, you can get other students to hold up mini whiteboards with the letters V, I and R on. As you pull on the rope harder, the person holding the V raises their board. As the rope moves faster, the person holding the I raises their board. However, if you increase the grip, the person holding the R raises their board, and as the rope slows down, the I is lowered. So we're helping students get a qualitative feel for the relationship between current, potential difference and resistance. And from here, it's not hard to see that current is proportional to potential difference and inversely proportional to resistance. And then it's just a small hop to show that current is equal to potential difference divided by resistance. And by the way, as the current is always the dependent variable, I think it really helps understanding if we represent the relationship in this arrangement of I equals V over R rather than V equals IR. Now we're going to have a look at a parallel circuit. Here the top loop is the same circuit as I had before, with a 10 ohm resistor and a current of 0.9 amps. But I've also got a separate loop with another 10 ohm resistor below. I've also added another ammeter in the main circuit at the top. At the moment, the switch on the bottom is open, so we've just got current flowing through one loop, so the current at the top is 0.9 amps too. But watch what happens when I close the bottom switch. There is now 0.9 amps flowing through the lower loop, and here at the top those two currents add up to give a current of 1.8 amps. It often seems counterintuitive to students that as you add resistors the current increases, but each resistor in parallel provides another route for the current to take, a bit like opening an extra lane on a motorway. If I increase the resistance of the bottom resistor by a factor of 3 to 30 ohms, the current at the bottom has decreased by a factor of 3 to 0.3 amps, but the current in the loop above is unaffected. The current in the two branches are independent of one another and only depend on the potential difference of the cell and the resistance of that branch. And the current in the main circuit always adds up to the sum of that in the branches. In summary, remember that the current is the same all the way around a series circuit, but in parallel circuits, the current in the main circuit is a combination of the current in the branches, and the current in each branch depends on its resistance. I hope that's been a help in teaching about current. There is another film in the series about teaching potential difference.
Hope to see you again soon.